So what does that mean? We had the original point again. Original R and H was R dot H dot was given by what? 1 inch, and H is 5 inch, right? 1 and 5. Then we change to dr, the radius increasing 0.03 and decreasing by minus 0.1. Again, increasing, decreasing depends on sign, plus and minus. So now I'd like to see how the volume changes, right? So to get the volume changes, we have to find dV. Again, differentials. The dV, again, we have R and H, partial derivative with respect to R, VR, right? Times how they change in R direction, dr, correct? Then we move to H direction. Let's find the partial derivative H. Then I'd like to see how they change in height. That makes sense? Then we can see whether the volume increase and decrease. Sounds good. So now let's get VR, VH. Number one, let's get VR first. Find the derivative of this one with respect to R will be 2 pi R H. And let's get VH will be pi R squared. And this one is estimated or evaluated at the previous version. The previous version was R equal to 1, H equal to 5. So plug in R equal to 1 and H equal to 5 in this partial derivative. So VR in this case will be 2 times pi times 1 times 5. Good? It will be 10 pi. And VH will be pi times R squared, 1 squared, again same pi. That makes sense? Number two, now I'd like to measure the volume changes, dV, by plugging this one. So we have 10 pi in VR, 10 pi. How we change dr? 0.03, increasing. Good. And VH is pi plus pi. How we change? We change minus 0.1. Good. So let's calculate how the volume changes. So this one will be 0.3 pi minus 0.1 pi will be 0.2 pi. Okay, you are fired. Why? We have 0.2 pi increased volume. Does that make sense? So if I modify, okay, I suggest, okay, you should reduce the height by 0.1 and increase the radius. Then you can save money. Okay, let's do it. I create it and then put it, the soda in a new can. Then I have more volume. I lost more my materials. Okay, you should be fired. Go out. I have to find another mathematician who can calculate this one. That makes sense?
No.
Does that make sense?
They got to give you a second chance.
No, I don't want it. It's a company. High risk because you're a PhD in mathematics.
So you're basically saying to increase the volume, you would make the increase the height. So like you can get more if it's a taller can, basically.
Listen. So let me tell you the history. What they did so far. So by looking at this one, the important thing is proportion. This one can modify, right? The proportion, how they fast increasing or decreasing depends on this proportion, right? So VR, 10 pi. VH is pi, 10 times different. So which one is more efficient to change? R or H?
Repeat that.
The volume.
Repeat that again.
The H.
We have a different rate, radius and H. Radius is 10 pi. So if you decrease or increase, change your radius, it affects too much in your volume because we have a 10 pi compared to height. Height has just pi, 10 times different. This is much faster. That makes sense. So what they did so far, the Coca-Cola company or Pepsi company, they reduce radius small and small and small. They increase a little bit high, a little bit high. They save their money. So compare with 2 years old can and now reduce a little bit different. They keep making a little bit higher, but they just get smaller.
But so it keeps the same value then?
No,
Value?
no,
There's
different. Because H again, radius has more,
Yes.
10 times, 10 times than the height. If you reduce the same size, like 0.1, 0.1, then we are. Well, let's reduce 0.1 in radius, right? And increasing 0.1 height. You can save more money too.
Yeah, you can save money.
Because we have 10 times pi by 0.1, right?
Yes.
And 10 times, 1 times 0.1.
Yes.
So this is positive 0.1, negative 0.1. So you have what? Minus pi, you have 0.1 pi increase.
But how does that equal to value? Like
Again, volume is given by this formula.
Yes.
So we derived it. That the important thing is, again, this formula tells you the volume changes when you change your R and H from the previous version, right? Then I like to see this one. This one will tell you which one wins.
So you're saying if you have a negative pi, that is-
Negative pi means where? Where? The output, negative pi?
Yes.
Then we lost
You lost
our
value.
materials.
Like you. No, I'm saying
The volume,
like so you lost value, which means it'd be like less
material, less
yeah.
materials.
So you keep your job.
Yeah, it is.
No, I'm trying to say like to the actual fluid ounces in the actual drink.
Yeah.
I'm saying like if it's a negative pi, that means there'll be less drink in there. If it's positive, it means there's
Exactly.
more value in there.
Exactly.
Oh, okay.
So again, positive and negative, means what? The volume increase or decrease.
So then, this is related. Then how can they keep the same volume, almost similar, but like make it a taller can? Is that possible?
Yes, it is possible by choosing, for example, here, the example, right? I reduce 0.1 the radius, right?
Okay.
But we have a minus pi. I like to make compensate. Then I have to increase the height by 1 inch. Right. Right? Then they have this will be changed to pi, they will be cancelled out. Then we have a same volume as the previous one. But it looks different because the radius is small but height is big compared to this one, right? Different but same volume.
So
But the people doesn't want it, right? And the company owner doesn't want it. They want to make it look like similar. A little bit changes in the radius always. But they like to make a compensate, they make a little bit increase in height. That's why the cans keep increasing height, but the radius is getting smaller, smaller, smaller. Now
that's why you have those the Coke skinny cans.
yes, it is.
And then like have you seen these Cokes where like they'll have a large radius, but then like they'll be a little bit taller.
Yeah, that's what happened nowadays. Because of this one.
Is that all like
Smart
like
water.
is that actual like Coke has actual mathematicians that do this for them?
Yeah.
Or is it like computers?
That's mathematician first. Now it's computer everything because this is very simple like formula, right? Everybody can do that if somebody take a Cal3. But if you have a more complicated function like this, it's not always can. Like we have a different shape. How you make the value? Oh. Can you measure the value? Oh, mathematician can do it.
That's dope. That's pretty cool.
Make it simple.
So,
You
so,
got-
so is that why people go into like food science and then like drink science?
I don't know drink science or not. But this is one of the previous studies in the world problem. real world problem. So any question about these two? Can I move forward?
Yeah.
Okay, it's more interesting, right?
Yeah.
That's why you're studying applied mathematics now. So now, so this is about finding differences. The next question is, can you find the maximum and minimum? So you guys know how to find the maximum minimum, local max, local minimum, Cal1, right? So we have a similar one in Cal3 in 3D, not 1D, not 2D, in 3D. We call section 14.7, we call this thing. So what we have, so let's consider we have a certain mountain, right? This is like a space. Okay? So the question is, we have a peak and peak, right? In space. This is like in space, okay? 3D. Even though I put in 2D, this is what we call local max. Local maximum. As you know that. And this point must be local minimum. But if we consider, let's say, like saddle for horse, with what saddle is, right? This is like my saddle. So there is a point here. But this one, it looks like local minimum. But if you look at the other side, this one is like a local maximum. So this one is both local minimum and local maximum in different direction. So this is what we call saddle point. So this one doesn't happen in calculus 1 because we only need 2D. Saddle point cannot exist. But in 3D, there is a saddle point. So saddle point means what? If you look at one direction, it looks like local minimum or local maximum. If you look at other direction, then it changes to other local extreme value. So this is what we call saddle point. This one happens in 3D. That's why we're studying this local maximum, local minimum again in space. Question? Okay. So our goal is to find the local maximum, local minimum in space. Okay? In space. So where we can apply this one? The material science. We can measure, we can find the local maximum, local minimum, also wave equation, wave propagation, like acoustic sound wave, the acoustic wave, like a cell phone. You guys have a wave, right? We call acoustic wave. And also we have an ocean wave. Then I like to see whether I have peak or bottom one. Also we can measure this one in tornado, everything. We try to find the local maximum, local minimum point. But in calculus 1, what you did, you only did local maximum, local minimum to apply stock marketing. Right? Stock marketing. Stock increasing, decreasing. But here we do more general 3D, like weather situation. So there are so many places we can apply, but again, the basic stuff I've already finished it. But if you go to PhD program, and then you will see where I can apply these basic stuffs. But you need more advanced stuff, right? Like different method, and you will learn more in graduate program. And also from your advisor. Then you will become more professional. So local maximum, local minimum. Let me skip everything. You guys know what critical point? So if you have f of x, y, g is equal to 0, okay? And the critical point is given by partial derivative equal to 0. You have x dot, y dot, g dot, equal critical point. So this one is very similar to the critical point in Cal1. Again, the critical point in Cal1, the derivative equal to 0, right?
Right.
And find the x, that's my critical point. So in this case, we have a 3 derivative in different direction. Called partial derivative, right? The critical point, yes, it satisfies these conditions simultaneously. F of x equal to 0, F of y equal to 0. They should satisfy this equation like a system of linear equation. Then this is my critical point. So let's look at example how to find critical point. Starving. No time. So let's get the find critical point. Or f of x, y is given by, let's say, x squared plus y squared minus 4y plus 9. So let's get my critical point, okay? So since this one has a 2 dimension, x and y, it's not exactly the same as what we did in Cal1, it's different, but we'll try our partial derivative. Let's do this. So to get the critical point, when you plug in this one, then satisfy the partial derivative of x should be equal to 0, partial derivative of y must be equal to 0, right? It should both satisfy these two conditions. So let's do step by step. Let's get a partial derivative. F of x, 2x, f of y, 2y minus 4. Good? Okay? Good? So from the first one, let's say equal to 0 to get a critical point. So we have 2x equal to 0 from the f of x equal to 0. We can automatically get x equal to 0, right? Because 2x equal to 0 means x equal to 0. Should be. And from second, 2y minus 4 equal to 0. Yes. 2y is equal to 4. This implies y is equal to 2. So what we got? A point, x comma y, which is now 0, 2. This is my critical point. How was it? How was it? Not bad, right?
No.
Okay, why we study critical point? Why we need it? Let's
Looking
go
for
back to calculus 1.
look for
Okay, why we find critical point?
maximum, minimum.
Yeah, this is the location of the maximum and minimum, right? That's why we try to find a critical point. Let me modify example 2, same. So let's say x squared x plus xy plus y squared minus 4y, let's say, yes, set equal to 0. So this is my f of xy, okay? So the question is the same, find the critical point. So first of all, to get a critical point, we have to find each partial derivative, and that's set equal to 0, right? Fx, 2x plus 2y, good? That's set equal to 0. 2x.
2y.
Oh, this is 2y, 2x, right?
Yeah.
Plus 2y minus 4 is equal to 0. Wait,
No, 2x.
I need something more. I need something more. Let's change this one. 1/2. Then it should be 5. So this one will be y. Good? Good?
Yeah.
Is this okay? So what we have, we have to solve this equation. Again, my x, y satisfy both equation. It's like a system of equation. So from the first one, what we have, y will be minus x. But if you move x to the other side, y should be minus x. Now we're plugging back to here, because they satisfy this condition too. So 2x minus x minus 4 is equal to 0, right? Then we have x is equal to 4. I move this one aside. Then y, plugging back to this relationship, y must be minus 4. So we have 4 comma minus 4 is equal to 1. How was it finding critical point? Is this okay? So now let's move to second derivative test. You guys remember second derivative test in Cal1? Okay, we have a similar one. The second derivative. So let's xc, yc critical point. Okay? And then what happens? F of x plugging xc, yc must be equal to 0. And fy, xc, yc should be equal to 0. Right? Because this is critical point. If you plug in critical point, each derivative, then it should be 0. Because from each derivative equal to 0. Right? So, number 1. F of f had a local maximum. As this critical point, xc, yc, if second partial derivative less than 0 and the discriminant rather than 0. So let's say my discriminant d f of x, f of y minus f of y. You guys know what this means? So second partial derivative at given point. This is what we call D. Number 2, local minimum. At this critical point, if now let's change this one to positive. And same thing, D value should be positive. Number 3, now xc, yc is the saddle point.
Professor,
Yes?
is that a x to the 0
What do you
or
mean?
c?
But
Well, it says let x. Is that a subscript c?
this one?
Yeah. What is that?
Critical point.
Those are zeros?
Critical point.
Oh, critical. Okay.
Critical point.
I'm like, okay.
It's not 0. Critical point. Maybe it can be 0 sometime, depending on function. critical point.
Okay, that makes a lot of sense now.
Okay. Third point, if your D is this one, less than 0, automatic set point. So this is how we know it's a local maximum, local minimum, or set point from this second derivative test. Question? This is like a formula, right? That's what you did in Cal3 to determine this local maximum, local minimum at the critical point. Example number 3. Find the extreme value of f of xy given by xy minus x squared minus y squared minus 2x minus 2y plus 4. Okay, let's get it. So we have a certain f function, and then we have to look at the location first. Location of the local maximum, local minimum, right? In other words, critical point, right? And then we have to find the extreme value, local maximum, local minimum. Not yet. I'll give it to you later. I wrote it. So let's do. So again, to get the midstream value, first we should know the location. In other words, we have to find the critical point, right? So number 1, critical point. Let's get f of x, y minus 2x minus 2, f of y, x minus 2y minus 2. So this is my partial derivative. Let's set equal to 0. What I have, y equal to 2x plus 2 from the first equation, right? No, we don't have to do that. Yeah, y equal to 2x plus 2. And this one, we have x minus 2y is equal to, let's say minus 2 is equal to 0, right? Again, we have to solve this equation. It's a system of linear equation. So let's plug in y in here to get x value. So what I'm going to do, I plug y in the second equation, 2x plus 2 minus 2 is equal to 0, right? To get x value, let's simplify x minus 4x minus 4 minus 2 will be 0, minus 3x will be equal to 6, x equal to minus 2. That's what I have. And then we're plugging back to the first equation to get y value. So plug into the first one. So y will be 2 times minus 4 plus 2 minus 2. So we found my critical point minus 2 comma minus 2. That's my critical point. We just solved the system of linear equation. This equation, right? You guys know this one how to find it. So once you find it, now let's do test. Second derivative test. number 2, second derivative. So first of all, we have to find the second derivative, right? So f of xx. Let's take one more derivative, this one, with respect to x. That's my f of xx, right? So minus 2. F of yy. Find the derivative of this one with respect to y, one more. Minus 2. F of xy. Let's take the derivative of this one with respect to y, maybe 1. Oh, this is my partial derivative. So now, d, first we measure discriminant, right? F of xx, f of yy minus f of xy squared. So let's check this is positive or negative. If this is positive, then we move forward, local maximum, local minimum. If this is negative, it should be set at point, right? F of xx minus 2 times minus 2 minus 1 squared, right? So we have 4 minus 1 is 3, okay, positive. So what I did, I checked these two positive. Then should be local minimum, local maximum, depends on your f of xx. We know f of xx, no matter what it is, minus 2, negative, right? So look at that. Discriminant positive, f of xx is negative. It satisfies first condition, right? Therefore, by second derivative test, f of xy has a local maximum at my critical point is what? Minus 2, minus 2. How was it? My local maximum must be, we have to plug in minus 2 and 2 into the original function, right? So local maximum will be f of minus 2, minus 2 will be 4, minus 4, minus 4, plus 4, plus 4, plus 4. So if cancel out, we have 8. This is my local maximum value. The location, minus 2, minus 2. Local maximum value is 8. Example number 4. So I will ask you this type of problem in test number 3. Local maximum, local minimum. This will be our last example. And then we're going to move to Lagrange multiplier. Quick.
Lagrange multiplier.
Again, this is optimization problem. Why we find this one to find the maximum and minimum kind of optimization to save our materials. So if you have something materials, then I'd like to build some cone or something 3D shape, and like to see how much material I can, save. We should use local minimum or local maximum in space. So I will do slowly for this problem because you should understand this one first. Then I will change my function. So critical point is not always one. You may have a more critical point. So if you have a more critical point, we did in Cal1 too, right? Cal1 we have a more critical point, right? That we have a local maximum, local minimum, in different critical point.
Yeah.
This one will happen in the 3D anyway. So the critical point is not always one. Let's get it. First critical point. Partial derivative 6 minus 6x plus 6y equal to 0. From this one, I know y equal to x. This equation that I have it. Right? Let's look at the partial derivative with respect to y. 6y minus 6y squared plus 6x is equal to 0. Good? Good or not?
Yeah.
Good. So let's plug in x equal to y here, second equation, right? To get this one. So what I have is, let's plug in x equal to y. So what I have, 6y minus 6y squared plus 6y is equal to 0. Right? So let's simplify. We have 12y minus 6y squared is equal to 0. So 6y, that's my common factor, 2 minus y is equal to 0. So we can answer y equal to 0 or y equal to 2. We have a 2y value. So we can find, so when x equal to y equal to 0, by this relationship, x must be 0. When y equal to 2, x must be equal to 2. Right? So we have a 2 critical point. Zero, 0, 2, 2. So if you have a 2 critical point, then we have to estimate, or we have to apply the second derivative test each critical point.